Alright guys, in this video we're gonna get into chapter 2. Chapter 2, probability. We're talking about probabilities in this chapter, and we're gonna start with 2.1, sample spaces and events. In this section, we're gonna classify some basic definitions. First of all, let's take a look at the definition of experiment. An experiment is any activity or process whose outcome is subject to uncertainty. That's the definition of an experiment. And then next, let's take a look at the sample space. The sample space of an experiment denoted by S is the set of all possible outcomes of that experiment. So based on the definition here, if we want to find the sample space of an experiment, we want to find all of the possible outcomes of this experiment and put them in a set. Now let's take a look at example here. Example number 1. Let's say flip a fair coin. If we flip a fair coin, what kind of possible outcomes we're gonna have? Of course, it's gonna be head and tail. So the sample space S would be the set contains the head and tail. That's the sample space. Let's take a look at number 2. Let's say toss a fire die. So if toss a fire die, what kind of possible outcomes we're gonna have? Of course, it's gonna be 1, 2, 3, 4, 5, 6. So the sample space is gonna be 1, 2, 3, 4, 5, and 6. That's pretty much how to find the sample space of an experiment. Now, next definition. Event. An event is any collection or subset of outcomes contained in the sample space. As an event is simple if it contains or if it consists of exactly one outcome and compound. Oh, excuse me. And compound if it consists of more than one outcome. So basically, all in all, the event is just a subset of the simple space. Let's take a look at example. Let's say, of course, this is example 1 is corresponding to this example 1 over here. We're still talking about the flip a fair coin. If we flip a fair coin, the simple space could be head and tail. Now let's say event A is equal to the head. So of course, since event A is a subset of the sample space over here, so A is an event. And then event B could be, let's say, the tail. So since B is a subset of the sample space, so event B is an event. And then let's say C is head and tail. So even though over here C is equal to S, so of course C is a subset of S as well, so C is an event which contains both head and tail. And then let's take a look at example number 2. So we have sample space is equal to 1, 2, 3, 4, 5, 6. Okay, now I would say, okay, in this case, A is equal to, we only have one element 2 in the set, so A is an event because A is a subset of S. Or let's say B is equal to, the set contains 1, 3, and 5. Now we can tell B is a subset of the sample space over here as well, so B is an event, and so forth. Okay? Now, once this makes sense, the next section I would like to talk about is called set theory. Okay, set theory. Now, first of all, definition. The complement of an event A, denoted by A prime or AC. Actually, we got the C on the corner here, is the set of all outcomes in the simple space S that are not contained in A. So based on the definition here, if we want to find out the complement of an event A, first of all we gotta know the sample space, and then we wanna find all the outcomes in the space but are not contained in A. Now, for example, so in the previous example, we have the sample space is equal to, say, example. The sample space is 1, 2, 3, 4, 5, 6. And then we know the event B is 1, 3, 5. Then what is the B complement? We know that the B complement contains all the outcomes in the sample space, but not in the event B. So we're looking for the elements are in the space, but not in the event B. So they're going to be 2, 4, and 6. So the B complement over here is 2, 4, and 6. And I gotta say this, the definition or the notation of complement is super important in probabilities, okay? You gotta be very familiar to the definition of complement, and you gotta know how to find the complement of an event. Then, definition, the union of two events A and B denoted by A union B and read A or B. Is the event consisting of all outcomes that are either in A or in B or in both. In both events. That is, all outcomes in at least one of the events. So based on the definition here, the union of two events A and B, denoted by A union B and read A or B, is event consisting of all the outcomes that are either in A or in B or in both events. That is, all outcomes in at least one of the events. Now let's take a look at example here and see how to find the union of two events. Okay, I'll give that event A is equal to 2. Event B is the bracket 1, 3, 5. And event C is gotta be 1 here. So there's one thing I would like to emphasize is that the event gotta be in the form of a set. You cannot say A is equal to 2. This is not the event. Okay, this is not event. They gotta be in the form of the set like this. Now, once we know those 3 events, first of all, let's say what is A union B. So based on the definition gave above here, if we want to find A union B, we just need to combine the elements in A and B. So it's going to be 1, 2, 3, and 5. Now we can tell this 2 is coming from the event A, and the 1, 3, 5 are coming from the event B. Then let's say what is B union C. Now we can tell we have one in the event C and we have 1 in event B as well. So then we don't have to write the 1 twice. So the A union B in this case, or B union C or B or C in this case is gonna be 1, 3, and 5. we don't write 1 twice over here, okay? Because 1 is the element, the 1 in the C here is element of B as well. So the B union C is 1, 3, 5. And then let's take a look at what is, if I gave you that the sample space is 1, 2, 3, 4, 5, 6. Okay, that's the sample space. And we know A union B is 1, 2, 3, 5, and I want you to find the complement of A union B. So if we want to find out the complement of A union B, we want to find all of the outcomes in the sample space, but not in the A union B here, since we're looking for the complement, right? So what are not in the A union B? So they are going to be 4 and 6. So the complement of A union B is 4, 6. So that's pretty much the definition of the union. All right, next definition. The intersection. The intersection of two events A and B denoted by A intersection B and read A and B. Is the event consisting of all outcomes that are in both A and B. So based on the definition here, if we want to find out the intersection, we just need to find out the common part or the overlap part of A and B. Now, for example, so based on the events given here, let's see, let me just rewrite down. S is 1, 2, 3, 4, 5, 6. And event A, I don't know why this pops up. Event A is 2. Event B is 1, 3, 5. And event C is 1. Now let's take a look at A intersection B. So as what I just mentioned, if we want to find the intersection, the intersection of two events, we want to find out the common part of those two events, right? So are there anything? Do A and B have anything in common here? I don't think so. So basically, in this case, A intersection B would be nothing. So we call it empty set. This symbol is called empty set, okay? And then let's take a look at a B intersection C. What's in common between B and C? So the common part or the common element between B and C, I think is 1. So the B intersection is 1. And then what about the complement of A intersection B? We know that A intersection B is empty set. So the complement of the empty set would be all the outcomes in the sample space. So in this case, the complement of A intersection B would be equal to the sample space, which is 1, 2, 3, 4, 5, and 6. Next, what about the complement of B intersection C? So if we want to find out the complement of B intersection C, we want to find all the outcomes in the sample space, but not in not in B intersection C. So B intersection C is 1 here. So all the other outcomes in the space would be 2, 3, 4, 5, and 6. Okay. Next, definition. Let phi denote the non-event when A intersection B is empty set, A and B are said to be mutually exclusive or disjoint events. So the notation of disjoint events or the mutually exclusive events, of course, they are completely equivalent, and this is a very important notation in probability. Okay, so what does it mean? So if, let me draw a picture of here, the Venn diagram. So I gave the rectangle here, and this rectangle represents the whole sample space S. And if I gave you this circle represent event A, and this represent event B, and then the overlapping, the intersection part, this part represent A intersection B. That's how we find the A intersection B. And then the second case is, this is the sample space, and I gave you the event A like this and event B like this. And then I'm shading all A and B here. So in this case, the whole shaded part is A union B. Okay? And then let's take a look at this case. That's the sample space S, and I gave you the event. I'm sorry. I gave you the event A here, and then I'm shading outside, inside of the sample space, but outside of the circle A. Then this shaded part, or the whole shaded area outside of A but inside of the sample space is the A complement. And then if I have the sample space S, and I gave you A over here and B over here. Now in this case, A and B have nothing in common. So in this case, A intersection B would be equal to empty set. And we also say that A and B are disjoint. Events. So that's basically the relationship between A and B, or how to find A intersection B or A union B, or A complement, or when A and B are disjoint events. And actually this kind of graph, those four graphs over here, those four graphs are called a Venn diagram. Okay. Venn diagram. Okay. All right, that's pretty much all about this video.